So I'm going to present today an overview about our recent work in this field of industrial robotics and machine learning and some of the applications we have been working on. And in a lot of our work, we actually use ROS extensively, especially at the prototyping phase. So where it's really about focusing on the functionality and getting the best tools in place in order to make the deployment integration simple as possible. And for that, ROS is excellent. All right. So I have, of course, here this typical slide that contrasts the type of robotics that we have seen in the last decades, which is on the left-hand side. So the robots in industrial automation, highly successful. We have probably millions of them in factories all over the world. And then we have this new trend of artificial intelligence or machine learning. So basically, since the advent of deep learning, a little bit more than 10 years ago, there have been always the question, how can we bring those together? So if you look at all the success deep learning had in other domains, then the question arises: is there anything we can reuse that will enable new applications, make things easier in our robotics world? And this is really what a lot of our work is about. So this intersection of what we call AI-enabled robotics. All right, so as mentioned, so what does characterize traditional automation? Typically, the robots follow fixed pre-programmed routines in very structured environment. That typically means they're programmed once to follow specific waypoints, paths, trajectories, you name it. And then they just repeat this sequence. There might be a little bit logic that allows for some variation, but typically they're not able to reactively respond to some sensory readings. Often they don't even have sensors such as cameras or other sensors that will allow flexibility. The strand of an AI-enabled robotics that I just mentioned tries to loosen some of these assumptions, so to make things more generic, to allow actually robots to make higher level decisions with respect to their actions. So it's about really moving automation forward to autonomous systems, where we develop machines for some generic task, and then we leave it up to the machine how they act in an unstructured and dynamically changing environment. And this is, of course, deeply inspired by the way how biological organisms act. So humans, we typically sense, reason, and then act. So, and if you look at a lot of tasks in manufacturing that are not yet automated, those are typically tasks that require exactly this type of sensing, reasoning, action loop at various frequencies and difficulties. And what's really quite simple for humans, such as picking something up, is actually extremely hard for robots, as we all know. All right, so here's another slide that summarizes some of the aspects that I just described. So classical robotics deals with explicit programming. Data is often seen as signals. We deal with static tasks and procedures, and it's highly repetitive. And don't get me wrong, so that's a great paradigm that is applicable to a lot of use cases. It has served us very well over the last decades, and it will not go away. So here, the challenges are often how can we engineer those tasks easier? How can we integrate robots and software in a simpler way into existing workflows? So those are the challenges on the right-hand side. So there's still a lot of work for us to be done. And this is what's driving a lot today's robotics deployments, as you have also seen probably at the Automate show this week. And then on the other hand, there's basically this additional, let's call it additional pillar that addresses very different use cases. So it's not a competing paradigm. It's actually a new paradigm, which deals with skill-based programs or programming. So very structured data, tasks and procedures are dynamic, and it allows just for much higher degree of flexibility. So we're looking at all the tasks where the previously described sensing, reasoning, action loop can be deployed. So now the question is, how do we achieve actually such a cognitive behavior in robots? We need 3 ingredients. The first ingredient is, of course, perception, because if the world is variable, if the world is ever changing, we need to perceive these changes, and that's where sensors come in. So those can be cameras, tactile sensors, force-torque sensors. It's a field that has seen a lot of attention recently. So we know that over the last 10 years, RGBD cameras, so 3D cameras in general, have been dropping. So prices have been dropping there, and capabilities became better and better. Then for a couple of years now, we have also seen the same interest in tactile sensing, although it's not yet at a point where it's widely deployed anywhere. Then the second ingredient is, of course, reasoning. So all the sensory data that we are achieving needs to be used to derive actions, and this is usually also combined with some prior knowledge of the world. So a world model, for example, where we maintain a state of the world that is then continuously updated with the sensory readings. And then the third ingredient is the robot arm to execute the action with the respective end-of-arm tool. And I think especially in this area of end-of-arm tooling, there could be a lot of improvements. If we look at common off-the-shelf end-of-arm tools, those are usually Apparel jaw grippers or vacuum grippers, which are fairly limited for the use cases which we try to tackle with this robotics AI paradigm. And then another ingredient which we consider actually important is the democratization of this technology, which means we want to give these applications, these tools into the hand of automation engineers in the field. So not just deep learning experts who know how to train a neural network model, how to generate synthetic data for that. But it's really about making those accessible, because we do believe there is a lot of functionality that is already available, but it's just not accessible. And this is something we would also like to change, and that's an important aspect to drive this forward. And this is actually also where the ROS community plays an important part. All right, so what I'm gonna do next, I'm just gonna walk through 3 applications that we have worked on and that others have worked on that are particularly applicable or were solved by this robotics AI paradigm. So the first of it is piece picking, robotic piece picking. So piece picking, and here we see a use case example. It's everywhere. So we have tons of jobs, actually tens of millions of jobs all over the world where people do nothing but just piece picking. So here you see a photo where pretty much everything is automated except the act of picking. And that could be a typical warehouse or a typical situation that processes one of your packages that you ordered online. And if you think further about it, then you realize that picking is actually a very prevalent task. So machine tending can be seen as some type of picking, and many others. So there's there's actually a huge incentive to automate piece picking, and this is also reflected by market studies. So this is one of them, and you can either look at the dollar volume on the left-hand side or the quantities, but the story is basically the same. It shows you that the piece picking robot market, and this is just for warehouse automation, that it's actually quickly growing. And also, if you went to trade shows such as ProMat or in Chicago 2 months ago, LogiMat in Stuttgart a couple of weeks ago, you have seen that this field is actually fairly mature. So there are a lot of products that can solve these type of use cases. So piece picking for warehouse automation. Now, what made piece picking for warehouse automation difficult so far? It was the fact that you need to deal with potentially millions of objects, millions of SKUs, and you actually don't have any models. You don't have any prior knowledge of them. So you need to figure out how to pick things without actually knowing what you're going to pick at runtime. So you need to develop a skill just for picking. And this actually has been solved with AI methods, with deep learning methods. So probably one of the best known papers in this area was the DexNet paper by Ken Goldberg's group at UC Berkeley in 2017, where for the first time it was shown that supervised deep learning approach can actually outperform any non-deep learning approach for picking unknown objects. And then since then we saw a bunch of commercial solutions on the market. And we actually are offering a solution as well. So Siemens has a library for PLC called Semantic Robot Pick AI, which was released 2 months ago in March. And this is a library that is installed on our PLC module. It's robot agnostic, camera agnostic, and end-of-arm tool agnostic. And it allows you basically to pick any type of unknown objects, primarily in intralogistics application. Here's a video, so that was not the demonstrator at this trade show, but at LogiMat. And actually, it will also be shown at Automatica next month, I guess. So this is a typical application where robotics AI actually led to a breakthrough. So the robot encounters objects it has never seen before, does not require any prior knowledge, and then based on an RGB camera, we can compute grasp points on these objects. And here you see one grasp point that is shown on the UI, allowing basically the robot to pick and place different objects. And then one thing that is also actually quite interesting is the placing aspect. So for a long time, many people worked on picking of unknown objects. And then eventually everyone actually realized that you also need to do something with the objects after you pick it. And a lot of tasks or use cases require you to do more than just dropping them somewhere in a conveyor or in a bin. And yeah, one such use case is smart placing. So putting basically playing Tetris with the objects, so finding the gap and putting them together. Good. All right. So as mentioned, I'm gonna walk you through 3 different applications. This was one of them, robotic piece picking of unknown parts. Now, the second application I'm going to talk about is apparel manufacturing. So something very different, however, as impactful and meaningful as piece picking. And I'd like to motivate this part actually with a comparison with other industries. So if you look how automation and robotics transformed most of today's trillion-dollar industries over the last century, then we see actually how things were quite manual 100 years ago and today mostly automated. This applies to automotive. This applies to electronics. However, if you look at apparel manufacturing, that we actually see it's pretty much the same. So the way how things were done 100 years ago resembles a lot how things are done today. So in this case, the only difference is that the left-hand side is black and white photo and the right one is in color. And the reason for that is simply because manipulation of limb materials is really hard for automation and for robotics. So it's not that there's no research. There's actually quite a lot of research going on. So next week at ICRA, we will see again a lot of fundamental research in this space, manipulation of limb materials with robots. But nevertheless, so we didn't reach yet the point where this can be automated in the same way we did for in automotive or in aerospace or in electronics. So if you want, so this is one of the grand challenges right now of automation, if you look at the industry, because it's literally the last non-automated trillion-dollar industry. And it's also, you know, it has also somewhat of a regional component because, as you can imagine, there's hardly any apparel assembly anymore in the US or in Western Europe. All of that happens today in Southeast Asia because that's an industry that just always followed the cheapest labor cost. However, with the disruption of the supply chains and so on, there's actually a huge interest also to onshore those industries, both in Western Europe and also in the US. And one of the ways to do it is actually to introduce automation, because that's how you can cancel out the labor factor. If the labor ratio becomes small, then it doesn't actually really matter how high the cost of labor is. And we have been working in this field for some time with our partners who you see here. So with the ARM Institute primarily, but also with, for example, USC, SK Gupta's group, but also Roger, who I see here in the first row. And that's actually one of my favorite applications. It was or is our NI-enabled bottom hemming project. So just to give you the scale of the market. So 2 billion t-shirts are produced every single year worldwide. That's an $38 billion market. And there is one operation that has to be applied to every single t-shirt, and that's the bottom hemming operation. So if you look at a t-shirt, if you're wearing one right now, that at the bottom of your t-shirt, you'll see that the end is flapped around and there's a stitch. And this is how it's done. So on the left-hand side, is the video playing? Yeah. So you can see there are machines for that, but what you need to do is actually to put the t-shirt on the machine, and then the machine takes actually care of the rest, and it ejects the part as well. And this is done 2 billion times per year. So what we actually did, we again used a perception reasoning action loop to automate this operation with 2 robots. And that's actually now exactly the same operation, but automated. This is at Henderson Sewing in Alabama. And there are at two spots here we use machine vision. So first of all, the first one is to detect the features that allow us to pick the t-shirt. That's right here. And the second one is here, where we detect this loop. So because after picking up, every t-shirt shows a different loop that we see here. But this loop is actually so exactly this loop. It's actually crucial to understand this closed loop in order to derive the action that will put the t-shirt on the machine. And the interesting thing is you can use exactly the same approach for a related application, which is t-shirt printing. So a lot of t-shirts have a print, and it's pretty much the same interface, mechanical interface, which would be another 500 million t-shirts every year. And then my third application example, and again, that's another manipulation example, is a little bit more involved in terms of the actions that need to be performed. It's industrial assembly. So we have work that centers around reinforcement learning for insertions and assembly. And just to recap what reinforcement learning is about, it's basically letting the robot or the machine try things out, take different actions, and then learn from observations. So the robot takes an action, it gets a reward, which is basically telling it whether it was a good action or not. And based on this reward, the robot can refine its actions. And that's a nice approach if you don't want to or cannot express the robot program explicitly. And yeah, this is often the case when you deal with complicated contact use cases that have contacts and exhibit a lot of frictions, like insertions and assembly. And let me show you how it works. So this is the phase where the robot performs trial and errors and learns how to do the insertion. So it knows whether it succeeded or not after it tries the insertion. And whenever it succeeds, it knows that its actions were beneficial. So it reinforces the policy. And then, let me stop the left-hand video. So the interesting thing is that you can apply exactly the same program to a very different part without changing anything. And it works as well. And this is, of course, a great advantage because it completely removes reprogramming if you do product changeovers. So we can go from one type of assembly to another type of assembly without touching any code, without switching any program. It's exactly the same program. And so this is actually some of our work from a year or two ago, but next week at ICRA, we will show our newest results, which uses a similar use case, so connector assemblies, but is significantly more robust and much better. All right, then this concludes actually my 3 use cases. And let me summarize and provide a conclusion. So there are basically some use cases that are still not automated and that will greatly benefit from cognitive capabilities. So this science, reason, act paradigm. It will allow to deal with flexibility and uncertainty while at the same time reducing engineering and commissioning efforts, as we have seen in the last example. Then the skill of picking and placing seems to be the most mature. So picking and placing unknown parts, picking and placing parts that are randomly placed in a bin. However, even here, we are only in the beginning. So if you think about how many different picking and placing applications there are and how few of them have been automated in production, there's still a long way to go. So I'm pretty sure it will take us another at least 10 years to work on picking and placing. And then, of course, the overall driver for all of this, the advances in machine learning. So not just the ones we've seen in the last 10 years, but also the ones that are now coming up. For example, foundation models have been now very successful in solving NLP. And there are actually a lot of folks also working on applying foundation models to robotics to provide some type of common understanding and reasoning. And I'm pretty sure this will give us soon pretty great results here as well. And then the other trends is the reduction of the price reductions of hardware, so sensors and farm tools and robots that simply helps with the ROI calculation for our customers and with scaling. And as I mentioned, we use ROS a lot in our R&D work. And giving this trend of robotics AI, so combining machine learning, deep learning with robotics, we as a community should also think, how can we accelerate this trend? How can we provide additional tools that can help here for the various applications? So this concludes my talk, and I think we have a couple of minutes before the break. Thank you for listening, and I'm happy to take any questions.
I guess, actually, can I go first?
Yes.
Right, so obviously Siemens makes some hardware, right? So are you saying like, I mean, I don't know if you have insights or it's something you hear about, like, do the trends like will actually manifest in like, say, the products Siemens offers as well? Is that a trend you're seeing? You're able to offer lower cost solutions because of the advancements in, say, for instance, AI? Is that a trend you even see within Siemens?
Could you repeat the question? So
you meant in your summary, you had
Yeah.
the impact of AI potential and reduction of cost.
Yeah.
And obviously, like the real sense is a great example too,
Yeah.
right? Where it's
Mhm.
like, hey, I get now 3D perception and like
Yeah.
a couple $100 piece of hardware.
Yeah.
Are you seeing that trend as well in the products Siemens offers as well?
Yeah, absolutely. So, and there are two sides for that. So one of them is increased performance for the same price. And RealSense is a great example. We actually use RealSense cameras a lot. But we do also offer, for example, lower cost IPCs and PLCs as well, simply lowering the price for compute and industrial domains. So we have, for example, the IPC 127, which is a smaller, more cost-effective IPC, or the logo PLC, which is exactly this story. Thanks for asking that.
Another question: what kind of problem the aesthetic application that people product that you show? What do I need?
So the question is, what kind of hardware do I need to run the thematic robot pick AI? So you need a robot, and then to farm tool, a camera, for example, RealSense. But we are hardware agnostic. And then from Siemens, you would need either our PLC and then our small addition to the PLC that is basically a small Linux IPC, or just a Linux IPC. So that's all. No GPU.
Nice.
Great question. I forgot to mention that we actually do pre-training and simulation. So we do sim to real. We first pre-train in simulation, and then we transfer the policy. That's actually why it only takes a few rollouts. Otherwise, it would take much longer.
Is that an overnight thing or just immediate?
The simulation? I mean, the simulation takes probably an hour. But then the refining on the robot takes a couple of minutes. So the video was accelerated, but sped up. But I think it took 20 trials.
One more. Gosh.
Sure. So in a number of years ago, and I think that one you showed perfect as well. The reason you guys put this way.
You mean two finger?
Yeah.
Oh, you have a great memory. I think I remember you. It was in Chicago, right?
Yes, Chicago.
Yeah. So we actually offer both. So we Apparel, JAWS, and suction cups. It's just for bin picking, vacuum grippers are much more popular. It's easier to reach the object because you don't collide with surrounding objects when you try to get around the object you want to grasp. But we have both.